Hello, I am Modestas Vainoris and come from Vilnius University in Lithuania. I would like to thank everyone present and the special organizers for allowing me to give this talk. Today, my talk will focus on electrochemically deposited iron on copper foam as Fenton's reagent for catalytic breakdown of methyl orange. First of all, short outline of my talk. Water is a precious resource that is becoming scarce not only in underdeveloped countries. What is Fenton's reaction and advanced oxidation processes? A bit about electrochemical deposition of heterogeneous iron-copper foam catalyst, testing its activity using methyl orange dye solution, and the results we have obtained using this catalyst, namely discoloration time and mineralization degree. I will end my talk with short conclusions. Fresh water that is used everywhere in our daily lives is actually quite a scarce resource in the world. Only 2% of all water supply is fresh water, and most of it is locked in the ice, mostly in South and North Poles, and only 13% is readily available for easy access. The availability of clean and safe to drink water, as well as water for sanitation, was recognized by United Nations and was put on the list of Sustainable Development Goals for the second time. Trying to preserve our precious freshwater reserves, we have to keep them clean, preventing dangerous substances from entering them along with wastewater. According to UN data, in low-income countries, most of the wastewater is released and treated. However, this is still an acute problem even in high-income countries where around one-third of the wastewater is released untreated. This is causing a serious harm to the ecosystems around the globe. And even treated wastewater is rarely reused in industry, only around 20% of it is reused. Our main focus was on the wastewater generated by textile, paper-making and printing industries that contains azo dyes, which account for around 60 to 70% of the all dye groups. The fast fashion has taken a serious foothold in the world, and we can see a sharp rise in textile and clothing consumption. This rise in consumption means also an increase in production and in turn generation of wastewater. The regulations have tightened, and in turn wastewater treatment is becoming a real problem where efficient and fast solutions are needed. Over the years, various physical techniques like coagulation, adsorption, reverse osmosis, chemical, like ozonation and chlorination, and also recent anaerobic biodegradation techniques have been developed to remove various pollutants. One of the best known is Fenton's reaction, discovered by H.G.H. Fenton in 1894. Traditionally, Fenton's reaction is considered to be a reaction between iron 2 ions and hydrogen peroxide, where highly active hydroxyl radicals are produced. These radicals later are used for dye oxidation. Trying to increase the activity of Fenton's process, advanced oxidation processes have been developed where classical processes combined with UV illumination, ultrasound generation, or simple use of other transitional metals. Usually such techniques show much higher efficiency and mineralization degree than classical Fenton's reaction, however, they are much more costly. Trying to increase the activity of classical Fenton's reaction, we have electrochemically deposited iron anti-copper foams using environmentally friendly electrolyte consisting out of iron 3 sulfate, glycolic acid, and citric acid. We investigated the morphology of foam deposits using scanning electron microscope, images which you can see in the first figure. We have investigated the effects that deposition potential and deposition time has on morphology of the deposits. Deposition time was controlled by varying the amount of charge that was passed through the cell. On the top row you can see increasing potential effects. Formation of more porous and better covered surface. On the bottom row we can see the effect of deposition time. With the increase of the deposition time, or in turn amount of coulombs, the surface develops more uneven bumps which could further increase the surface area and in turn activity of the catalyst. Current efficiency calculations have been made using grammatical data and can be seen in Figure 2. The deposition was performed using magnetic steering bar rotating at 600 rotations per minute. The overall efficiency of the deposition, regardless of the potential applied, did not exceed 30%. The cause for this probably is the absorption of the organic matter on the working electrode, effectively blocking the surface of the electrode. Increasing the potential, the efficiency of the deposition slightly increases. At low potentials, the current density is quite low and the iron is heavily complexed with citrates and glycolates, hence the deposition is quite slow. As the deposition time increases, the deposition efficiency drops regardless of the potential used. The cause for this decrease is probably quite vigorous mixing. The flow of the solution breaks apart the dendrite-like structure on the surface, especially so with the longer depositions. Fenton's reactions, basic principles. pH, concentration of pollutant, and ratio between iron 2+ and hydrogen peroxide all have an effect on the overall rate of the breakdown reaction. Recommended pH range for Fenton reaction is around 2 to 3, where there is a constant supply of iron 2 ions. At higher pH, 4 to 5, the formation of iron hydroxides occurs, which are insoluble in water, that form a sludge which later has to be removed. However, heterogeneous catalysts recommend this problem. There are 5 main reactions governing the total rate of the breakdown. The first 2 produce highly oxidative hydroxyl and hydroperoxyl radicals. Hydroxyl radical is much more desirable since it has much higher oxidation potential. The other 3 reactions scavenge these radicals, reducing the efficiency of the main reaction, the dioxidation reaction. Also, since we are using copper foams, copper corrosion also occurs. Copper ions can help to regenerate the very desirable iron 2 ions, which help to generate the hydroxyl radicals. As I mentioned earlier, we used methyl orange as model nitro dye. We chose to use quite high concentrations of methyl orange, trying to simulate overall organic content in wastewater. Fenton's reaction or Fenton-like reactions usually are used where the TOC is around 20 milligrams per liter. We use solutions with pH 3, which was under constant agitation using magnetic steering bar rotating at 600 rotations per minute. In here, you can see a full scheme of methyl orange breakdown. However, the first step is the one where the methyl orange solution loses its color. Full mineralization of methyl orange occurs in at least 6 steps, requiring a lot higher amounts of hydrogen peroxide. We tested what effect iron deposition potential and deposition time, or charge pass, has on the solution's discoloration time. The discoloration was tracked using UV visible light spectrophotometer. Typical light absorption dependence was measured from 620 to 320 nanometers, trying to prevent UV illumination and in turn agitation of hydrogen peroxide breakdown. The mean peak is around 480 to 490 nanometers and is related to chromophoric double nitrogen bond in methyl orange. Measurements were done every minute. The start of the measurement was suggested so that the ending would be as close to the discoloration time as possible. As we can see from the data, that with increasing the potential, the discoloration rate increases and the time becomes short. This is caused by bumpy deposits obtained using higher potentials. Also, further increase the discoloration rate can be achieved by increasing the amount of iron on the foam. At around 450 coulombs, the minimum can be reached and the discoloration time does not change afterwards much. This is the result of enough iron and very fast corrosion of iron on the highly porous copper foam surface. Next, we investigated what effect methyl orange amount in the solution has on discoloration time. For these measurements, we chose the highest potential since the discoloration time, on average, was the lowest across the board. Looking at the dependence from the amount of iron, we see a similar picture as in the previous case. In this case, it's much clearer that using higher concentrations of methyl orange, around 450 coulombs, a maximum breakdown rate is reached. Also, as we can see, there is no linear relationship between methyl orange amount and discoloration time, meaning that our chosen ratio can break down even larger amounts of organic matter in water. We have also investigated what effects solution's temperature has on the discoloration and mineralization rates. The discoloration rate, as expected, increases with the increase of the temperature. The best result we managed to achieve was discoloration of 100 milliliters of solution containing 100 milligrams per liter methyl orange in 90 seconds. We have also looked how the temperature influences mineralization's efficiency. And as we can see, the best result was achieved using 40 degrees Celsius, where in 10 minutes we managed to mineralize around 30% of all the organic material in the solution. And finally, conclusions. The combination of electrochemically deposited iron onto high surface area copper foams show a great activity in Fenton-like reaction. The highest discoloration rate was achieved using highest potential for deposition at 50 degrees Celsius, where 10 milligrams of methyl orange solution was discolored in 90 seconds. We have also found that at higher temperatures, the first step in methyl orange mineralization increases with the temperature. However, the peak mineralization efficiency overall was achieved at 40 degrees Celsius. Also, we have found that both surface area and the amount of iron that has been deposited on it influence the overall breakdown rate of methyl orange. I would like to thank everyone for their attention and European Union for sponsoring this research. Thank you.